mostly going to be people about the scalar product of vectors, or what is called dot product, and couple of its applications. As I said, you will get the result of your major test either today or another day or so, and along with the result you will also get the question paper and the solutions of that. However, if any doubt persists in any of the questions, you can always discuss with me later. So let's start with the session as the people are still joining in. So mainly today's session is going to be about dot product or scalar product of vectors. But before that, we will start with one more additional concept, which is related to vectors in 3 dimensions, or the component representation of vectors in 3 dimensions, and that is the concept of something called direction cosines. Okay. Direction cosines for a vector in 3-dimensional component notation. So we develop a system of notation like this, that if a particular vector which has been expressed in the 3D component form, so these are a mutually perpendicular x, y, and z axis. So this is the negative z axis, this is the negative x axis, like that. Now suppose we have a particular vector which is 3-dimensional, so it's not lying in any of the planes. Neither it's lying in the xy plane or the yz plane, or nor on the zx plane, but it's just generally out there somewhere like this. Now first of all, we denote the angles that it makes with the 3 axes: the positive x-axis, the positive y-axis, and the positive z-axis. Those angles are denoted by the special symbols alpha with respect to x-axis, beta with respect to y-axis, and gamma with respect to z-axis. So we use the symbols alpha, beta, and gamma. Still have people joining anyway. So alpha is the angle. So wait a minute. Before that, if I've expressed the vector for the vector E, which is some x component into I cap plus y component into j cap plus z component into k cap. Alpha is the angle of the vector E with respect to the positive x-axis, or you can simply say with respect to I cap, because the unit vector along the positive x-axis is I cap. Okay? Similarly, we use the symbol beta to express the angle of E with respect to the positive y-axis, or j cap. And similarly, we use the symbol gamma to express the angle of vector A with respect to z-axis. So the term cos alpha, cos beta, and cos gamma, these 3 terms collectively, they are called the direction cosines, because they help us visualize the direction of the vector. So they are called the direction cosines of the vector with respect to xyz axis. Okay. So the reason why we define direction cosine is because there's an easy way to express it in terms of a formula. Okay. There's an easy way to express it in terms of a formula which can be calculated once we know the components of the vector. And once we have found out the direction cosines, obviously from that we can find out alpha, beta, and gamma, any other operation which is required like sine alpha, tan alpha, etc. can be calculated. But you'll see in a moment why we start by defining the direction cosines, because they are easy to calculate from a direct formula. Just make a note of the definition first. So this is the definition of direction cosines. Collectively, they are called the three direction cosines: cos alpha, cos beta, and cos gamma. And collectively, they represent the geometry of that vector. Now, next moment, we are going to see the formula to express it. So first, just make a note of this concept. So we use the standard symbols alpha, beta, and gamma to express the angles of the vector A with respect to the positive x-axis or I cap, the positive y-axis or j cap, and the positive z-axis or k. So those of you joined in late just now, we just about started. So if you start by writing down these definitions, you're more or less up to date on what has happened in the lecture so far. Oh, now we'll see something interesting. What happens is, in terms of a formula, cos alpha is simply given by the x component of A divided by its magnitude. Cos beta is simply given by the y component of the vector divided by its magnitude. And cos gamma is given by similarly the z component divided by its magnitude, where we understand what we mean by capital A here is actually modulus of the vector or root of x component square plus y component square plus z component square. So I'll give you the justification of this formula in just a moment, but first you note down these as a formula. They're very easy to understand geometrically. There's a Q hota hai, why the value of cos alpha should be so much, cos beta so much. That we'll understand geometrically very easily if we just interpret the vector E in terms of that, it is the body diagonal of a cuboid of sides ax, ay, z. If you interpret it that way and try to understand what these angles should be, it's very easy to justify why the why the direction cosines are given by this particular formula. Okay. Yeah, so any questions so far? Yes, I've got a couple of questions. Yes, just about the. Yeah, Hardik, what is I want to write down on it. Yeah, I'll show you the previous slide. Just a moment. Okay. All right, so let's first look at some application of this. Then we'll come back to the justification of the formula, etc. So, for example, if I have vector E given by this formula, it is root 2 I cap minus root 2 j cap plus 2 k cap. And we want to find the direction cosines of the vector A. And eventually from that, we also want to find out the angles alpha, beta, and gamma. And nothing but the angles with respect to x, y, and z axis. Standard meaning of alpha, beta. So in a situation like this, all we have to do is apply the formula. So you can see above lot of people joining in late. Anyway. Yes, good, Dharmil, that is correct. Now check the algebraic sign. Okay, make sure that AX, AY, and AZ are with sign. In this question, what is happening is that Dharmil, your first and third are correct. Second one, you have here. Magnitude of the vector E is square root of root 2 square plus root 2 square. Here the minus sign is not important because you're squaring it. Magnitude, as you know. So mod of the vector is square root of E, or you can write that as E root 2. Okay. Therefore, cos alpha, which is AX by E, is 1 by 2. Cos beta, however, is minus 1 by 2. Yes. No, it's 60 beta because cos inverse of half is not 30, it is 60. Yes, Arnav, that is correct. So EY by A will be minus half. Because remember, EY was minus root 2, whereas EX was positive. Okay. So this is where we have to be mindful of the sign. Be really careful in a question like this. Just a moment. Okay. And cos gamma, which is Ez upon P, we are becoming 1 by root 2. Remember Ez. So that's your first part. These are your direction cosines. Cos alpha, cos beta, and cos gamma. Now your second part is finding out the angle itself. So cos alpha is equal to 1 by 2 means that alpha is 60 degrees. And you can also express this as pi by 3, as you remember. Cos beta is minus half. So that means beta is actually 120 degrees. Or 2 pi by 3. And cos gamma is 1 by root 2. That means gamma is 40. So you have to understand this thing that if a direction cosine is positive, that means that angle is active. If direction cosine along some particular direction happens to be negative, that means that particular angle is obtuse. And of course, there is also the special case that if direction cosine with particular axis is 0, that means the angle made with that particular axis is 90 degrees. Here, just for reference, I used alpha, but it can apply to beta and gamma also. Okay, so hope this question is clear to everyone. Okay, good. Yeah, so that is the thing. Saying 60 degrees is the same thing as saying 300 degrees, but it's like, here alpha, beta, and gamma are the angles between two directions. The direction of the vector A and the direction of I cap, or the direction of vector B, vector A and J cap. Similarly, and K cap, the positive x-axis, positive y, and positive z. So it's just taken as the direction. I mean, it's just taken as the angle between two vector arrows. So we always express it as the smaller of the two angles. We don't really use the anti-clockwise and clockwise configuration anymore. So there is no sense in taking 300 degrees. Okay. So what this will mean in terms of diagram also we will interpret. Okay, but before that, let us also look at another couple of questions and see how it makes sense. Now similarly, find direction cosines and alpha, beta, gamma for now these following vectors. So first let's visualize these two vectors with their direction cosines. Then we'll get a little bit more clarity about how the formula itself comes and how the diagram of a vector looks with the given three angles alpha, beta, gamma. You can see why these two examples are a little bit easier because they have one component missing each. That means they lie in a particular Cartesian plane. The vector A, for example, you can see it lies on the xy plane. The vector B, you can see lies on the xz plane. So these vectors are a little bit easier to visualize now. Yes, Dharmil is correct. And what about cos gamma? Yes, Aditya, correct. Good. That's correct, Dharmil. So for the first example, you can see that magnitude of the vector E is 2. Ex is √3 and Ey is -1. Therefore, cos alpha is √3/2. It also tells you that alpha is 30 degrees or pi/6. And also Ez, of course, is 0. That also. Cos beta, on the other hand, is -1/2. So that means also that your beta is 120 degrees or 2 pi/3. And cos gamma is 0. It means that gamma is 90 degrees. Now this one should have been obvious because you can see that the vector E lies in the xy plane. So obviously that means it is perpendicular to the z-axis. So it's easier to visualize this vector now for us because we don't have to draw a three-dimensional system. We have to just understand that the vector E is in this xy plane only. And somewhere here. Is it? You can see that the angle it is making with the x-axis is 30 degrees, but the angle it is making with the y-axis, that's your alpha. So as I told you that in the case of alpha, beta, and gamma, there is no sign convention. We don't talk clockwise, anti-clockwise. Beta is 120 degrees, but gamma is 90 degrees. Because the vector E, because z-axis is perpendicular to the plane of the diagonal. So here we don't take clockwise, anti-clockwise and all that, because we are just taking the angle between the vector E and I cap, which is the x-axis, positive x-axis. We're just taking the angle between the vector E and j cap. So we won't take the angle with respect to the x-axis as this one like this and make it 330 degrees. We just take this magnitude of the smaller angle, which is 30 degrees. Okay, so hope this is clear. Now similarly, the second one, 2i cap plus 2k cap. You can see that the magnitude of the vector v is 2 root 2. The x component is 2. The y component is 0. And the z component is 2 again. Okay. You can see that this vector, it lies in the xz plane. Correct, that's good. So if it lies in the xz plane, it is perpendicular to which axis? To the y-axis. So we should be getting beta as 90 degrees. Okay. Let's check out. Okay, so cos alpha dx upon b is 1 by root. That means alpha is an acute angle 45 degrees. Cos beta, as expected earlier, is coming 0. So beta is 90 degrees. And cos gamma is also coming 1 by root 2. So pi by 4 we can express this as. We should also get used to the system of denoting angles in terms of radians, which I'm sure you would have learned about in trigonometry and maths. Pi radians is equivalent to 180 degrees. So now if we visualize this, we can think like this, that suppose this is our XYZ coordinate system. Now this is the XZ plane. So this vector actually lies in this plane. So now if we look directly into this, a line of sight is that we're looking directly into the XZ plane like this. Then for us, the XZ plane would look something like this. Looking straight into this, we can see that like this, and y-axis would be coming out perpendicular to the plane. In this diagram, it would look like this. In this diagram, how would the vector v be looking like? The vector v would be looking like something like this. This would be a vector v, such that this angle gamma is 45 degrees. This angle alpha is also 45 degrees. But because it's perpendicular to this plane, our beta is 90. So back in this diagram, it's lying somewhere here, but you have to understand it's lying in this plane, in the exact plane. So the vector v is lying like this, such that it is perpendicular to the y-axis, whereas this angle and this angle are 45 degrees. Okay, people. So hope this is clear so far. Okay, good. So now let us understand a couple of more important things related to direction cosines before we move on to the important thing for the day, which is going to be component, dot product or scalar product. Right. Now, one important property of direction cosines. Actually, it's an important identity related to direction cosines. That is this, that if you sum their squares, then it has to be unity. So this is an important property of direction cosine, that sum of their squares is equal to unity. In words, we can write this identity as sum of the squares of direction cosines of a vector always equals unity. And it's not too difficult to understand this from the formula. Okay, the proof of this is very simple. The left hand side, which is cos square alpha plus cos square beta plus cos square gamma. If you just express each of the direction cosines in terms of the components and magnitude, so it is ax upon a whole square plus ay upon a whole square. Now it must be obvious to you. Just take the common denominator e square, and in the numerator you have the sum of the squares of the components. So that's nothing but the magnitude square itself. So it's ax square plus ey square plus ez square, which you know by definition is nothing but e. That is the right answer. So as long as we are okay with the formula of the direction cosine, that cos alpha is ax by e, cos beta is ey by e, and cos gamma is ez by e. This totally makes sense. And you can also check out for the 2 or 3 questions we have done that this identity will hold true for the direction cosines that we got over there. Now, this also implies something pretty obvious, that suppose we have a special vector for which one of the direction cosines equals 0, because one of the angles with a particular axis is 90 degrees. So it's the vector is actually lying in one of our rectangular Cartesian planes. So in that case, what happens? The sum of the squares of the other 2 direction cosines become 1. That means the other 2 angles are such that they are supplementary. So that also happens. So also, if for example gamma is equal to 90 degrees, or cos gamma is equal to 0, that means cos square alpha plus cos square beta must be equal to unity, which means that alpha plus beta must be equal to 90 degrees. So basically, this is talking about a vector in the xy plane. If a vector lies in the xy plane, then obviously it is lying such that the sum of this angle and this angle has to be 90 degrees, or the sum of the squares has to be unique. Similarly, if some other angle is 90, like alpha is 90, then cos square beta plus cos square gamma will be unity. So beta and gamma will have that unity. And the vector will lie in the yz plane. And similarly, zx plane for another one. Okay, so this is how we can reduce it to vectors which are actually lying in two-dimensional planes from the general relation for the direction cosines. So just minimize this for you so you can see the whole thing. Okay. Now let us understand the geometrical interpretation of direction cosines. So this is again something fairly easy. So if we just visualize a vector as we had done earlier, it just represents the body diagonal of a cuboid which has edges equal to each of the components. You just do a simple interpretation like that of a vector. So let us say we have selected this corner as our origin. So this is our y-axis, this is our x-axis, and this is our z-axis. So this side is ax. So this thing as a vector would be ax I cap. This thing as a vector would be ay j cap, and this thing as a vector would be az j cap. But now our given vector, which is the sum of these three components, ax, ay, and az, is this one. Now imagine what I'm trying to do is I'm trying to find the angle with respect to one of these axes. So for example, I want to find out the angle for my vector E with respect to y-axis. So I want to find out, let's say I want to find out the angle beta geometrically. So I would just want to find out this angle. So to find out this angle, what I can do is I can just join these 2 points here and draw a right angle triangle. So if this point is the corner point, let's say it was E or something, and this is the corner point B, whereas this is the corner point E. So this point's coordinates would have been Ex, 0, 0. Likewise, this point B's coordinates would have been 0, Ey, 0. And this point E's coordinates would have been Ex, Ey, Ez, because it's lying on the opposite body diagonal of the origin. So like that. So now let us look at this triangle OEB. Now it might not be obvious in the diagram over here, but the triangle OEB is actually a right angle triangle, where these two sides, the side OB and the side BE, are perpendicular to each other. This angle here is actually 90. Now why that angle is 90 is because you can see the side BE is the face diagonal on which face? On the face which is parallel to the XZ plane. Okay, you can see that this one. This and this are parallel lines. So BE is actually lying parallel to the exact plane. So it has to be perpendicular to the y-axis. So in this triangle, this angle OBE is equal to 90 degrees, because you can see OB is along the y-axis and BE, which is a face diagonal, is parallel to the exact plane. So that is why now if I change my line of sight, I visualize this triangle from this side like this. So if my line of sight is now like this, then I will be seeing that triangle like this one. And this would be my vector E, and this angle would be my beta, and this would be E. You can see that cos beta is equal to base upon hypotenuse. So that formula. So likewise, you can draw perpendiculars on the x-axis, the y-axis, etc., and understand the other components also. But this is a geometrical way of interpreting the direction cosines and understanding that you can make equivalent right angle triangles with respect to each of the axes and understand the direction cosines with each of them. So for example, if you join this corner point E with the point E, so that triangle EOE that you get, that will again be a right angle triangle. And that will help you establish why cos alpha will come out to be AX upon mod. Okay. And similarly, if you take this corner point here as C or something, okay. Similarly, triangle OCE, that will also be a right angle triangle. And from that, you can establish why cos gamma will be EZ by E. So this is all about the interpretation of 3D geometry in that kind of sense, in that visual kind of sense, where you always interpret the vector A as the body diagonal of a cuboid like this, from the origin to the vertically opposite side, such that each of the edges of the cuboid are respectively your AX I cap, AY J cap, and AZ K cap. Okay, people, so hope this is fully clear. So for us, more important right now than the geometrical interpretation is the formula itself. How for a given vector we find the direction cosines using those particular relations, that cos alpha is AX upon EM. Similarly for cos beta and cos gamma. So these formulas. Okay, so having done direction cosines now, let us come to the second part of today's lecture, which is extremely important, which is a new operation for us in vectors, which is called the scalar product of two vectors. Or it is sometimes referred to also as the dot product. You'll understand very soon the logic of the nomenclature, why it is called scalar product or why it is called dot product. It is called dot product because the symbol used for it, the symbol for this operation That symbol is simply a dot. That's one reason why it's also called the dot product. And the definition of the dot product is that if we operate dot on two vectors, so it will be read as scalar product of A and B, or in short form it will just be read as A dot of B. It is given by the formula AB cos theta. Okay. So the scalar product of A and B, in short we can just read it as A dot of B or A dot B. It is given by this formula where A is nothing but magnitude of the vector A, B is nothing but the magnitude of the vector B, and most importantly theta is the angle between A and B. It is not anything to do with the axis. It is just to do with the two vectors A and B. It is the angle between the vectors. So at this stage, it's not about the logic of why the formula is like this. It is just a new definition for us, an operation which is given by this particular formula. Product of the magnitudes into cosine of the angle. Now the logic of this again we'll understand when we look at the interpretation, especially when we see the interpretation from the point of view of physical applications. When we understand, for example, that how we can calculate work done by a force using a dot product between the force vector and the displacement vector, then we'll understand the logic of why it is AB cos theta and why it is not simply AB or AB sin theta or something like that. There is a very well-defined logic why the formula involves cos theta. So this is, yes, Nikita, don't worry, I will be sending you the notes also. Okay, so this is the definition of the scalar product, or what we simply read as A dot B. Okay, so it's pretty simple really. Okay, so let's look at a simple geometrical example. So suppose we are just giving three arbitrary vectors. E is a vector of magnitude 10 units. B is a vector like this. Now let us say. So magnitude 20 units. But B is drawn in a direction such that to extend A's line of action, this angle is, let us say, 60 degrees. And now we have another vector, let us say C, like this. Like the vector C like this. That's also magnitude 10, but there this angle is 30 degrees. So we just have to find E dot B, B dot C, and E dot C. Let's find the E. So just use the formula over here to find out each of these. The definition of the formula is that the product of the magnitude is the cosine of the angle between them. Yes, Dharmil, good. The first one is correct. Correct, Rakshan. Good. Yes, Shubham, correct. Snikita, correct. Pritesh, correct. Manas, correct. Amok, correct. Correct for the second one, Amok. Dharmil, both your answers are correct. Arnav, correct. Yes, Aman, your third answer is also correct. Oh, but Aman, you have to check the algebraic sign on the third one. So see, you have to understand here that if you draw the vectors from a common origin, the vector B, for example, it lies over here. But the vector C actually lies like this. You can see something very interesting here. That because this angle will be 30. Because over here you can see this angle was 30. And this angle is 60. So interestingly, the vectors B and C are perpendicular to each other. The angle between B and C is 90. The angle between A and B is 60. But also the angle between A and C, this angle, is how much? 120 degrees. So these are the angles you'll have to use for each of the dot products. So when you're doing A dot B, the angle in consideration will be the angle between the vector B and the vector A, which is 60 degrees. But when you're doing B dot C, the angle between B and C will be this one, which is 90. And similarly, when you're doing A dot C, the angle will be this obtuse angle. The direction of C is like this. And the direction of A is like this. So between them, there is an obtuse angle, which is 120. Oh, sorry, 150. My mistake. Correct. Please make a correction here. This angle will be 150. This angle here is 30. Okay, so anyway, so by formula now, when we come to A dot B, it will be magnitude of A into magnitude of B into cos of the angle between them, which is 60. So it is 10 into 20 into half, which is 100 square units. Because each of them are in the same unit, so it will become square units. Whereas when we took B dot C, you see it will become BC cos 90 degrees, which in fact becomes 0. Doesn't matter what magnitude of B and C are because cos 90 is 0. And similarly, when we take E dot C, it will be product of magnitudes into cos of 150 degrees. So that will become again 10 into 20 into minus, as you remember, cos 150 is the same as minus cos 30, which is the same as, we have to make use of that. So this will become minus of 100. So these are my final answers. And it is also in square units. Oh, C का value 10 है. Sorry, my mistake. So if I've taken C as 10, then correction here. It will become minus of. Okay, thank you. So is that correct? Is that clear now? So from this we are also seeing something that the dot product of two vectors can also be negative, and of course it can always be zero also. Zero when they are perpendicular vectors, negative when they are at an obtuse angle, and positive only when they are at an acute angle. So that is why, for example, in a later chapter we'll see work energy theorem. A force can end up doing negative work on a body because the displacement might be making an obtuse angle. A force can also do zero work on a body because the displacement of that body might be perpendicular to the direction along which the force is acting. So if, for example, we are applying a vertical force but the body is moving horizontally, then the work done by that force will be zero because the dot product of force and displacement will be zero. Why? Because the angle between them is 90. Right, people. So hope this is clear for you. Good. Okay, now let us see some important properties of this operation or the scalar product operation, which becomes obvious from the definition itself. We know the definition of scalar product is that the magnitude of vector A multiplied by magnitude of vector B multiplied by cosine of the angle between. So the first property is that the scalar product operation results in a scalar quantity. It's very simple because the the right hand side is a scalar. It is the product of EB cos theta. So mod A is a scalar quantity. The magnitude of a vector is a scalar, and cos of any angle is just a number, so it's a scalar. So it's the product of three scalar quantities. So what does the operation result in? It results in a quantity. The output of the operation is a quantity which is a scalar, and that is why, in fact, it is called scalar product. And the second property, which is very obvious from it, is that E dot B is positive for theta being acute. It is negative for theta being obtuse, and zero when they are perpendicular, or theta is 90 degrees. So dot product of perpendicular vectors is 0. A very important special property to remember. That if two vectors are perpendicular to each other, their dot product will be 0. So that is two important properties. Now, another important property, I'll give you time to note down, don't worry, is that A dot B equals B dot U, which is obvious from the definition. Because A dot B by definition is AB cos theta. And likewise, B dot A by definition would be B into A, but into cosine of the same angle. So they have to be the same. So in other words, this is what we call a commutative property. It is a commutative operation. For example, other operations like sum is also commutative. Okay. But difference of two quantities is not commutative. Similarly, multiplication of two quantities in scalar algebra is commutative, but division of two quantities is not commutative. So commutative operations are operations where the two variables we are operating on are interchangeable and it takes no result. So A's operation with B, if it is the same thing as B's operation with P, then we call the particular operation as commutative. And as you can see, the way dot product is defined or the way scalar product is defined, it is by definition and a commutative kind of operation. Okay. So just make a quick note of this, then we'll see the next two properties. Okay, so hope you've written this down. Now, just a continuation of these properties. After theta is 90 degrees, this one, yeah. Dot product of two vectors which are perpendicular to each other will be 0. Dot product of perpendicular vectors is 0. That is the last point which I have written. Now another important property of dot product is that it is what we call distributive. That means if we take dot product of A with the sum of B and C, that can be expressed as dot product of A with B plus dot product of A with C. For example, in normal algebra, multiplication is a distributive property. So this property is called distributive property. Multiplication and division are both distributive properties. Yeah, Manas, the thing is the scalar quantity can be negative. That's not a problem over here. Because, for example, in your regular physical quantities in physics, electric charge is a scalar quantity, but it can be negative and positive. Similarly, just the coordinate of a particle on any axis, like the x coordinate, that quantity is a scalar quantity. It's not a vector quantity, okay, but it can be negative or positive. So certain scalars just have magnitude. Certain scalars have magnitude with algebraic sign, positive or negative. So that's not a problem. Okay. For example, if I just give you the number minus 50 centimeters or minus 50 seconds, the time difference, let's say, between your motion and my motion is minus 50 seconds. So, but time is still a scalar quantity. So, attaching a negative sign to a number into a unit does not mean that we have necessarily converted it to a vector. That does not mean that. In one-dimensional motion, of course, we use a shorthand notation for vectors by using algebraic sign. So, instead of writing a vector as positive of x I cap or minus of x I cap, we just remove the I cap from our notation. So, there the positive or negative sign sort of hints that we are talking about a vector quantity, even though we are not using the unit vectors in 1D motion in kinematics. But that is again like a short form notation. Okay, so that is the important thing. So because you're used to, in 1D kinematics, vector quantities being expressed in terms of sign, but you might be thinking that, okay, if something has algebraic sign, it becomes a vector, but that's not necessarily. All right, so distributive property, I think, is fairly obvious. Now, the next thing which is important for us is that a dot product of a vector with itself is nothing but square of its magnitude. Very simple. E dot E is nothing but magnitude of A into magnitude of A into cosine of 0. Because the angle that a vector makes with itself is 0 degrees. So that becomes easy. So now we'll see something interesting, that if you put together some of these properties, like the property number 2, which tells us that perpendicular vectors give a scalar product of 0, and the distributive property, okay, and this property over here, we'll see something interesting. You will get the formula from here for dot product in component form or in component notation. So before we can attempt dot product in component notation, let's understand one important thing, that unit vectors, I caps dot product with itself will be unity because of this. Similarly, J caps dot product with itself will be unity. K caps dot product with self will be unity. But I caps dot product with J cap will be 0. J caps dot product with K cap will be 0, as will be I and K. And this comes from the second property, that if we have perpendicular vectors, their dot product must be 0 because cos 90 is 0. So these two things that we've written, the relationship for dot product of our standard unit vectors, these are actually coming from the application of properties 2 and 5 that you've written about. Now add to that the distributive property and it becomes very obvious. For example, if I have a vector like this, 2 I cap, and another vector B, which is let us say 3 I cap plus 2 J cap. And I ask you find A dot B. So here we will not go with the definition method that A dot B is equal to AB cos theta. So that will become too lengthy. First we need to find out A, then we need to find out B, then we need to find out angle. So many things are known. Rather we will use the properties of vector. So we'll substitute A as its given value in component form, and same for B. So we'll substitute. And next we will use property number 4, I think, which is the distributive property. Yeah, property number 4, which is the distributive property. So next we just open this bracket. So this is 2 I cap dot product with 3 I cap plus 2 I cap dot product with 2 J cap. So we can write this as 6 into I cap dot I cap, which we know is UDT. But also here 4 into I cap dot J cap, which we know is 0. Now we use the properties above of unit vectors. We see this becomes 6 plus 0, or it becomes 6. So we'll also develop a general formula using the same concept in terms of the general components Ax, Ay, and Az, in case we have both the vectors 3-dimensional. But this is the logic of how we calculate dot product of vectors which are given in component form. You can understood. Good. So if we just generalize this now. So we just the general formula for dot product in component form will be, if I now substitute the vectors A and B as the sum of 3 individual components. Now see, when we next use the distributive property, we will actually have a total of 9 terms, not 3 into 3. But out of those 9 terms, which terms will survive? The ones which are having I cap dot I cap, J cap dot J cap, and K cap dot K cap. And which terms will get cancelled out because the product is 0. I cap dot J cap, I cap dot K cap. We'll use that set of identities. That I cap dot I cap is 1. J cap dot J cap is 1. But for example, I cap dot J cap is 0. J cap dot K cap is 0. So using those 6 identities, okay. So here we'll see the first term here, dot product with the first term in the second bracket actually gives us AX into BX. Because I cap dot I cap is unit. But the second term, I mean the second term of the whole expression, which is AX I cap dot product with the second term in this bracket, that has a term of I cap dot J cap. So that results in 0. Similarly, the third thing also results in 0. Similarly, when I now take AY J cap dot product with these, the dot product with the first term is 0, but the second term gives you AY BY. And the third term similarly gives you 0 then. Now again, K cap dot product with I cap and J cap is 0. So you're left with just K cap dot K cap. So that becomes the product of EZ. So from now on, whenever we are using component notation, instead of the definition formula AB cos theta, the formula that we use is this. That dot product of two vectors is product of their x components plus product of their y components plus product of their z components. So very, very simple interpretation. So this now becomes like a definition or a formula for dot product in component form. Okay, so let's just look at a very basic example. If I have the vector E, let us say as I cap minus J cap plus K cap, and the vector B as 2I cap plus 2J cap minus K cap. And I ask you to find out A dot B. So just apply this above formula and you'll see you get A dot B as the product of the x components. You can just directly write them 1 into 2 plus the product of the y components. But don't forget the algebraic signs if any. So minus 1 into plus 2 plus the product of the z component, which is 1 into minus 1. So this is becoming 2 minus 2 minus 1. So it's in fact minus 1. And as we know, dot product can be positive, negative, or zero. Depends on the relationship between the vectors. So let's do another type of simple exercise related to this. Now suppose the information is given to us geometrically in terms of all our vectors lying on a two-dimensional xy plane. So this is vector E and it is of magnitude 50, and this angle here is, let us say, 37 degrees. Then our vector B, let us say, is like this, and its magnitude is 20, and our vector C, let us say, like this, its magnitude is also 20, but this angle is now 30 degrees. So all magnitudes are in some common unit. See, so we want to find E dot B and E dot C, and also but each of these we want to find by using the first case, the standard formula, and the second by using component notation and the component form of vectors. So this question can be done by both ways. We can, from the geometry shown, we can find out the angles involved and we can do this, or we can convert the given vectors into components. So all the vectors here shown lie in the xy plane. So they are actually two-dimensional xy vectors, and all the magnitudes are in some common unit. So you can do both parts of this question A and B by two different methods. So try it out by both the methods and verify the answers that you get. Yeah, just to answer your query, you will be getting the major test question paper along with the results. In fact, with that, you will also be getting solutions. But still, if you have some queries in any of the questions after going through the solutions, also you can always send them to me and I'll help you out. Yeah, Amog, it is correct. The first answer that you got. No, Yashovardhan, you have to check your answer. Chinmay, it's correct. Manas is correct. Sorry, Yashovardhan, it's correct. Aditya, you have to check your answer. Be careful about the angle. Dharmil and Aditya, both of you, be careful of the angle between A and B. It is not 37. Oh, just one thing, people. Instead of E dot C, which also we can calculate, it's not a big deal, but calculate B dot C. Manas, correct? You will get the marks of your minor test, of your major test this week itself. Okay. So let us draw the vectors in relation to one another. So this was the vector E. In comparison to that, the vector B. Like this. And in comparison to these two, the vector C in some sort of direction like this. Okay, so this diagram is making sense, I hope. Okay. You can see that this angle was given to us as 37 degrees. That means the angle between A and B, this becomes 53 degrees. And also for C, this angle was given to us as 30. So the angle between B and C, this one becomes 60 degrees. Also the magnitude of A was 50 units. The magnitude of B was 30, 20. And the magnitude of C was again 20 units. Okay. So if I am solving this geometrically now or directly from the formula, you can see that E dot B will be EB cos 53 because between the vector E and the vector B, you can see the angle is 53. So that is 50 into 20 into cos 53 is 3 by 5. That becomes 600, whatever that unit was square. And similarly, B dot C becomes BC cos 60 degrees. Because the angle between B and C is B. Open text. Yeah, lost connectivity. So coming here, lost my connectivity. Okay. So people, I think problem is sorted out now. I had got logged out, and then when I logged in, I was not able to make myself the host and unmute my. Anyway, so hope everything is, yeah, looks like everything is okay now. Right, so coming back to this question we were discussing. Okay. So we now want to calculate this quantity. So we will use the distributive property. So we will first calculate this as the sum of A dot B plus A dot C. Okay. Now A dot B we have already found out. A dot C is the quantity that we need to calculate now. Now that's going to be a little different the way we do the calculation of A dot C. So for A dot C, we'll understand that the vector E lying like this and the vector C lying somewhere like this. So you can see that with respect to our y-axis, this one was 53 degrees and this one was 60 degrees. So the angle between them, the theta, between A and C, this angle is actually 60 plus 53 degrees. Or it is 113 degrees. Now, I'm not sure if you are aware of this formula. Do you know this formula? Cos A plus B is equal to cos A cos B minus sin A sin B. Do people know this formula? Yes, good. So we can make use of this. So from that you can see that cos theta, which is cos of 60 plus 53, can be written as cos 60 into cos 53 minus sin 60 into sin 53. So this will become 3 by 5 into half minus 4 by 5 into root 3 by 2. So we can write this as 3 minus 4 root 3 by 10. So this will in fact become a negative quantity, as you can see, because it's an obtuse angle. So the numerator is negative. Okay. So we'll use that now. Okay. So for A dot C, we'll have AC cos theta, where the magnitudes of A and C were 50 and 20 respectively. So 50 into 20 into, now that will become that quantity, 3 minus 4 root 3 by 10. So that is 100 into 3 minus 4 root 3. That is our A dot C. Or actually, if you want to understand it more properly, A dot C is a negative quantity, which is equal to minus of 100 into 4 root 3 minus 3. These many units squared. So that is our A dot C. Okay. And now we go back to what we are calculating in the second part, which was A dot B plus A dot C. So we see that therefore A dot of B plus C, which should be A dot B plus A dot C. Now this becomes, now we'd seen earlier that A dot B was plus 600, and just now we are seeing A dot C is minus 100 into 4 root 3 minus 3. So this will actually become 900 minus 400 root 3. Climbing up. Okay. So this should become our final answer for the second part. A dot B plus C. So fairly lengthy calculation, especially because we had to make use of that special formula of cos A plus B. So I'll just show you all the steps. And A dot B, of course, I've got from the first step. Okay, so from part 1, A dot B was 600. So I'm using that. So hope this is clear. Okay. Now let us understand this whole question. So, don't worry about the lengthiness of the calculation. We'll see by component method, this can be done more easily. Okay. So we can also do this question by component method. And we'll be able to verify the answer also once we do it by component method. So by component method, what will happen is we can write these vectors very easily in I cap J cap notation. So for example, the vector E was like this. Of magnitude 50. So the vector E in component form should be 40 I cap plus 30 J cap. That's correct, because we are using the values cos 37 is 4 by 5 and sin 37 is 3 by 5. It's pretty easy. Okay. Similarly, the vector B is directly lying along the y-axis. So we don't even need to resolve it. It's already resolved. Something like this. (20 units along the y-axis. So the vector B is 20 J cap. So you can see the dot product with A will give you 600. But before that, let's also work out the vector C. So vector C is now like this. C is also of magnitude 20, but this angle is 30. So the vector C should be written as, we'll have a negative x component of cos 150, so that is minus root 3 by 2. So minus 10 root 3. And a positive y component of sine 150 is half, so plus 10. So we are making use of the fact here that cos of 150 degrees is minus root 3 by 2 and sine of 150 is plus half. We are making use of this. Okay. So now once I've got A, B, C in component form, it's very easy to calculate each of the things. So A dot B is just, they're two dimensional, so we'll reduce this formula to two dimensional. Okay. So Ax into Bx is 0 because Bx itself is 0 and Ay into By is just becoming 600. So this is positive of 600. Okay. Similarly, B dot C, you can see is Bx Cx plus By into Cy. So again, Bx is 0, but By is 20 into 10, so that's 200. So plus 200. Okay, which are the same as the answers we had got above. This and this. Of course, this is same unit square. And now when we come to this part, E dot B plus C, what we can do is first we can find B plus C. So B plus C is, B was 20 J cap and C we just now saw is minus 10 root 3 I cap plus 10 J cap. So this is going to become minus 10 root 3 I cap plus 30 J. Okay, so this is my B plus C. So substitute that over here. So this becomes, A was how much? A was 40 I cap plus 30 J cap. Dot product with B plus C now, which I will substitute as this. So that is okay. So that becomes product of X components. So that is minus 400 root 3 plus product of Y components. So that's 900. So there you go. Therefore, you can take 100 common or whatever, it doesn't matter. But this becomes this answer, which you can see will match the earlier answer we had written. This. Okay. So anyway, I'm just going to leave you with the steps for a little bit. In component method, what we do is we first resolve the vectors A, B, and C into the component form, so called. And then we substitute in whatever operations we are doing involving the dot product. Okay. So, I mean, might be lengthy at places because there are a lot of small little calculations involved, but they're all like logical steps where you're just, you're just step by step applying a systematic method. So there's nothing really tricky about it. It's just about having patience and completing the calculation. The tricky part of vector algebra we have mostly finished actually. Okay, so now the few things which are remaining, like dot product today, which we are covering, and also cross product, which we'll see later. They are just new types of operations where we just have to understand how to do the applications based on their definition. Okay, people, so hope this is clear to all of you. Okay, so people, hope this is all clear. Yes. Okay, so now we look at scalar product has a lot of different applications, both in physics and maths. So, for example, in physics, a direct application of scalar product is we use it to calculate work done. So we'll come to that later. But today, to wind up, we'll see one more very interesting application of scalar product, and that is something that we've been talking about for a while now. How to calculate the angle between two vectors given in component form, now using the scalar product. Okay, so method to calculate the angle, let's say theta, between two vectors A and B given in component notation. Okay, but using the dot product method. So we learn to do this using dot product method. So this is like a reverse application. Okay, since the definition of A dot B is magnitude of A into magnitude of B into cos theta. So if we invert this definition, cos theta is nothing but the dot product of A and B divided by the product of their magnitudes. So anytime two vectors are given to us in component form, okay, this is very easy to calculate. So given A and B in components, we know that A dot B is given by a simple formula, AX BX plus AY BY plus product of Z components. Okay. And similarly, we know that magnitude of A is this simple formula. So in my final formula which I have written for cos theta, you can see on the right hand side that numerator is nothing but this quantity. The denominator is nothing but the product of these two quantities. So it's all formula. There's nothing else we have to do. We don't really have to develop any logic or anything for this. We have to just substitute the values given in the given question with these formulas. Okay. So for example, so first just make a review of this and make sure you understand this whole thing. Just a minute. So this is the method that we will now, from now onwards, we will prefer this method for calculating the angle between two vectors. when the vectors are given in component form. This will be the preferred method. And as you can see, this method is giving us even for 3D. Whereas earlier anything we have developed as a method, it cannot be used for 3D. Okay. So basically we are just inverting this formula. And in this, the numerator on the right hand side is just calculated by this. The denominator is just calculated as the product of these three. So we know cos theta. And then from that we can calculate the value of theta. Calculate how much theta is converted. So let's just wind this up with a couple of examples. So let's start with one example which is very, very easy to interpret. If I have the vector E, which is suppose 2i cap plus 2j cap. Now I have the vector B, which is 3j cap. And I ask you what is the angle between them. Between the vectors A and B. Now you can actually directly understand this because the vectors are lying in the xy plane, and you can see because A is having same x and y component, so A is actually bisecting the first quadrant. So it's pretty obvious that the vector E like this, where this angle is 45. In the same diagram, you can see the vector B is also pretty obvious. The vector B is lying along the y-axis, but it has just a j cap. So you know that this angle has to be 45. But let's check it out by the dot product method. Okay. So cos theta is equal to E dot B divided by EB, where E dot B is EX into BX, so that is 2 into 0, plus EY into BY, so that is 2 into 3, plus the Z components anyway 0. And magnitude of A is 2 root 2, you can see directly, and magnitude of B is 3. So this is becoming 6, upon 2 root 2 into 3. So that is 1 by root 2. So cos theta is 1 by root 2. So it's obvious that the angle is 45. So this was just a testing sort of problem, so that we can see what is happening geometrically and agree with that by what is happening with dot product method. But the real value of the dot product method is where it is not easy to draw geometrically the vectors because they might be 3-dimensional. There we can see that the dot product method becomes the only method for us to calculate the angle. This minute I'm first. Yeah. Okay. So understood the method. You calculate A dot B by using the components AX, BX plus AY, BY plus AZ, BZ. And of course, you know how to calculate the magnitude of the vectors. So it's like this. Okay, now as a second and final example, if I take vectors which are now 3-dimensional. So let's say the vector E is 2i cap plus 2j cap, whereas the vector B, let us say I cap plus j cap plus k cap. Now there is no way we can draw these vectors. We want to find out theta. Okay. So there is no geometrical method. Because what is happening is we can individually find out the angles of A and B with x, y, and z axis, but that is not going to help us in finding the angle between A and B because they are not lying in any particular plane. This one is lying in the xy plane, but this one is general three-dimensional. So there's no way we can get the angle directly. So we have to use the formula cos theta is equal to A dot B divided by mod A into mod. Now again, A dot B you can see is 2 into 1 plus 2 into 1 plus 0 into 1. So that's why A dot B. So that's how much? 2 plus 2, 4. And mod A is square root of 2 square plus 2 square. And mod B is square root of 1 square plus 1 square plus 1 square. So this becomes root of 8 into root of 3. So this will become 2 by root 6 or square root of 2 by 3. Oh, sorry, square root of So we will now, since this is not a known value like that, so we just say that cos theta is equal to root 2 by 3, or theta we will say is cos inverse of that value, root 3 by 2 by 3. Okay, so hope this is clear to all of you. So unfortunately, I have again got logged out on the other whiteboard screen, so I'm not able to write the final step. Just write that as theta will become cos inverse of square root of 2 by 3. Okay. Or finish writing down up to here, and I'll help you with the last step. Okay, so is it clear up to this one? So our final step here will become this. I'm just putting it on another whiteboard for you. So our final step will become like this, that theta Okay, people, unfortunately not having great luck with the whiteboards in this last minute of our lecture. So anyway, what you do is you just write down the final step. So your final step will become like this, that your theta should be cos inverse of, in bracket, write down root 2 by 3. That just becomes your final answer. Okay. So anyway, so hope this was clear up to this point today's lecture. So with this, we complete today's lecture, and I will send you a worksheet which will be specifically based on application of dot product, formulae, etc. that we've done today, and finding the angle between two vectors, which is another important indirect application of dot product. And plus, now will be a good time to start working out some revision questions for the part that we've done earlier in vectors from your module, since we've completed the regular worksheets. So I'll also send you a list of questions later today, or to complete from the module also. That is the useful mathematics of physics module, which has vectors in it. Okay. So that's it for today, people. Hope you've understood this lecture. I'll send you the recording and the whiteboard. Okay. And your result for your major test will be coming up within a day or two. So best of luck with that, though I'm sure all of you have done pretty well. Okay. So that's it. Bye, people. Yeah, today, tomorrow, I mean, I said within a day. That's why we get the result within a day.